So the previous class, we were looking at convex optimization problems. I introduced some basic definitions, how we formulate what is a general form of an optimization problem. So we'd say that it is in standard form if you have to minimize some function f of x subject to a bunch of inequality and equality constraints. And these constraints define what I call a constraint set or a feasible set. And the problem is said to be feasible if the constraint set is non-empty. And it's said to be solvable if this minimizes, there is actually an x which achieves the minimum of this particular function subject to those constraints. So we also defined a bunch of other terms, such as what it means for a point to be epsilon suboptimal, right? And we also defined what a local optimum is. And then we looked at this problem of statistical estimation. The goal is the following: there's a parameter x that we want to estimate, but then we don't get to see x, we get to see another quantity which is y, and which is called the observable, and the related probabilistic rate. So conditioned on a particular value of x, y is distributed according to p y given x. And generally speaking, we'll assume that x and y are continuous random variables. So they're arbitrary real valued or vector valued quantities. So we assume that p y given x, that is, this conditional distribution, is known, and at least we may or may not make the assumption that x is also random and distributed according to px. But in the special case where x and y are discrete, one can ask for the estimator for x given y that minimizes the probability of error. And that turns out to be the maximum a posteriori probability estimate, or the MAP estimate, which is obtained by maximizing p of x comma y over all possible x. If we know certain other if there are some other constraints on x, then one can look at the constraint maximization of p of x given x comma y. Right? So the quantity p y given x, you can write p of x comma y as p y given x times p of x. So p of y given x in statistics is commonly called the likelihood function. So how likely is y to occur given that x was the actual true value? And log p of y given x is called the log likelihood function. So the problem of map estimation can also be formulated as one of maximizing log p of x comma y. Right? So I also define what it means for a distribution to be log concave. So a distribution p of x is said to be log concave if log p of x is concave. Right? So the log of the distribution of the density function is concave. Right? We looked at some examples of log concave distributions. So the Gaussian, the Laplace distribution, the uniform distribution, these are all log concave distributions. Right? So now let's look at this. Let's go back to the problem of estimating x from y. Right? Suppose that the distribution p of x is uniform. Right? Or sometimes, what if we don't know what the distribution on x is? So in these cases, commonly people use the following estimator for x. So the maximum likelihood estimator is the following. So given the observation y, the maximum likelihood estimate of x is defined as the argmax overall x of p of y given x. It's not p of x comma y. Now this is some estimator, right? I'm not claiming that this is good in any sense, in any particular sense. Uh, but one point to note here is that there is no prior on x. I'm not saying that x is a random variable or I know the distribution of x. So if x is uniformly distributed over some set, let's call it script x, then this maximization problem, it essentially turns out to be the same as the map estimation problem. And that is simply because p of x is just, it's uniformly, x is uniformly distributed over the set script x. So maximizing p of x comma y is the same as maximizing p of y given x, because you only have an additional constant term. So this is a constrained maximization problem, and if p of y given x is concave, then you can actually do this maximization. But instead, you can also look at the maximization problem. Argmax belongs to some set of log p of y given x. So instead of maximizing the likelihood function, I can try to maximize the log likelihood function. And now if log p of y given x is concave, then I can use some kind of a convex solver to find this maximizer. Right? So again, I'm not going to talk a lot about the ML estimator. If you take a course on, say, detection theory or estimation theory or even statistical inference, then you'll see that the ML estimator has several nice properties. So it is in some sense can asymptotically consistent, and there are a lot of other very nice properties. But we won't get into that in this particular course. So let's look at some examples, specific examples of ML estimation problems. So let's look at the following problem of linear measurements, of estimation from linear measurements. So suppose that there's some vector x that we want to estimate, but our observations are linear perturbations of the true x. So a1, a2, a3 up to am are all vectors which are known to us. Y1, Y2 up to Ym are called the M measurements. And Z1, Z2 up to Zm are basically noise random variables. They're all assumed to be IID, and we know the distribution of Z. Right? So again, also write this as Y is equal to some matrix A times X plus z, where x is an n-dimensional vector, A is an m by n matrix, and z is a random vector with IID components. Z is basically noise. Yes. So this is a very standard problem studied in machine learning, statistics, communications. So in communications, this, for example, the A could be the channel coefficients, Z is additive noise, and Y is what you observe at the receiver. There are, or for example, in some basic problems in image processing, A could be some kind of a transformation that you do on your image or your signal, and Y is your observation, and Z is some additional noise, so on and so forth. Right? It's a very general model. It's been studied for decades, and the goal is still to what is the best estimator for X given the measurements Y. So let's look at one example where Z is IID Gaussian. Let's say mean 0, variance sigma square. What is the maximum likelihood estimator reduced to? Can we get a more simple form? Right? So recall that the ML estimator for X is equal to log P by given X. So maximization of argmax overall X of log of Py given X. What is Py given X equal to? Sorry, can you Ax plus Z log Py given X? Okay, what is the distribution of Y given X? So Y is equal to Ax plus Z, right? Here that Z is Gaussian. So what is Y? The distribution of Y? It's Gaussian with what mean, what covariance matrix? The mean is, why is it A transpose X? Okay, yeah. So in this case, I'm assuming that it's A times X plus C. So it's mean. The mean is A times X, and the variance is, what is the covariance matrix? So it's the same as the covariance matrix of Z, which is sigma square times the identity matrix. So what does this reduce to? Over X. What is the PDF of additional PDF of Y given X? Yeah. The dimensional Gaussian value. Correct. What is it equal to? It's 1 over 2 pi sigma square whole raised to n by 2 e raised to minus, yeah, no, x square by 2 sigma square. Huh, what is it? Okay, covariance matrix is anyway this time. Yeah. So what does it reduce to? Norm of x minus
y minus ax.
y minus ax square by 2 sigma square. Does this reduce to a problem that you've seen before? Yeah. Okay. More specifically, can you tell me what is the least squares problem that this reduces to? So all of these are constants which don't really depend on x. So we're only interested in that part of the function which depends on x, because everything else is just either a scaling factor or a shift. We don't really care. What we want is the argmax. That's it, right? So maximizing this function, so log is of course monotone. I have e raised to minus y minus ax the whole square by 2 sigma square. So maximizing this quantity is the same as minimizing norm of y minus ax the whole square. Do you all agree? So this is just arg min over all x norm of y minus ax the whole square, or arg min of norm y minus ax. This is a convex function, and therefore it's a convex optimization. Okay, so now instead, if I assume that z is has a Laplace distribution, right? So it is 1 by 2 alpha e raised to minus mod x. So each zi has distribution zi by 2 alpha. What does the ML estimated reduce to? Yeah. Ah, mod zi divided by. Sorry, can you speak up? What do you mean by mod y minus ax? So y and x are vectors. So what do you mean by mod of y minus ax? Norm? What norm? What norm of a y minus ax? L1 norm. Okay. So what is the distribution of y given x? It is 1 over 2 alpha full power n e power minus. So in other words, it's summation I equal to 1 to n of absolute value of zi by alpha, which is also equal to yi minus ai transpose x divided by 2 alpha, or 1 by 2 alpha raised to the n e raised to minus the L1 norm of y minus ax divided by alpha. Alpha should be alpha. And basically, you get this summation because it's a product of conditional distributions. So this is in fact 1 over its product I going from 1 through n of 1 over 2 alpha e raised to minus absolute value of yi minus ai transpose x divided by alpha. So, so what does the maximum likelihood estimation problem reduce to? Yeah, correct. So it's basically an L1 norm minimization problem. Now, what if I take Zi to be the uniform distribution? Say from minus alpha to alpha. Yeah. Check. Sorry. Yes. Even I'm not. Yes. Yes. What would be a range of values? Yeah. So there's no unique minimization. That's what you're trying to say. Correct. So it's a constant. Yes. So P y given x is whatever, it's a constant. If
y belongs from x minus alpha.
okay, y is in
X minus
ax. Yi is in ai transpose x.
So y minus x is infinity not would be less than.
Yeah, why?
Y minus ax,
Correct.
it's infinity now.
Uh-huh.
Like the maximum value should be
Correct. Less than or equal to.
between minus.
So p y given x is, you can rewrite this as 1 over 2 alpha whole raised to the n if the maximum overall I, 1 less than or equal to I less than or equal to n of yi minus ai transpose x is less than or equal to alpha, or the same as saying that the infinity norm of y minus is less than or equal to. Okay, so but what is the optimization problem reduced? Okay, is that xml is
This would be one of the possible.
it's one of the possible solutions. Is there a way of formulating it in a slightly different way? Yeah. Okay. So XML is admin overall x such that minus ax infinity norm is less than or equal to alpha of what is the objective function? Yeah.
Anything constant.
Yeah. Any constant. Right. So this is in fact a constraint satisfaction problem or a feasibility problem. Okay, so far we were looking at ML estimation problems, right? Where our only goal was to maximize P of y given x or log P of y given x. But now what if we have a map estimation problem? So, for example, in the previous case, let's take the linear measurement with IID noise problem, where we have y equal to a times x plus z, but now we also have this additional information that x is also Gaussian. It's distributed according to, it has a certain mean and a certain covariance matrix. Right, so you have y equal to ax plus z, where z is IID Gaussian with mean 0 and variance sigma square, and x is, let's say, IID Gaussian with mean mu and whatever variance p times r. Now we know that py given x is a log concave distribution, right? It's Gaussian. Px is also a log concave distribution. So maximizing log p of y given x is effectively it's a convex optimization problem. But what about the map estimation problem? So the map estimator is the argmax overall x of log px comma y. We know that each of these functions is convex or concave in this case. Log p of y given x is concave. Log p of x is also concave. And one thing to note is that the map estimate could be different from the ML estimate. Is this always guaranteed to be a convex optimization problem? So effectively what we have is the sum of two convex or two concave functions. Is the resulting function also guaranteed to be convex or concave? Whichever. Okay, and why is that the case? Let's say that they're convex. Then what kind of linear combinations is going to give us a convex function? Yeah. Okay. Does it have to be? Do alpha 1 plus alpha 2 have to sum up to 1? Yeah. Both non-negative. So let's look at this. So we have alpha 1 f1 of theta x1 plus 1 minus theta x2 plus alpha 2 f2 of theta x1 plus 1 minus theta x2, right? Now I want to claim that this should be less than or equal to alpha 1 theta f of x1 plus 1 minus theta f1 1 plus alpha 2 times theta f1 of f2 of x1 plus 1 minus theta f2 of x2 so that this would be equal to theta times alpha 1 f1 of x1 plus alpha 2 f2 of x1 plus 1 minus theta times alpha 1 f1 of x2 plus alpha 2 f2 of x2. So this is what we want. We want for if this function has to be convex, then this quantity should be less than or equal to this quantity for all x1, x2 in the domain and theta between 0 and 1. But when can you say that this is always true? If alpha 1 and alpha 2 are non-negative, then certainly this is the case. Now, it could be the case that for some alpha 1 and alpha 2, where one of them is negative, this could still be a convex function. But if you want a more general statement, if you want it to hold for all f1 and f2, then alpha 1 and alpha 2 being non-negative is suffices. Okay, so now what other operations would preserve convexity? So suppose that f is convex, f is an Rn to R, and A is an n by m matrix. B is an Rn. What can you say about f of Ax plus B? Is this going to be convex? Yeah. And why? Okay. So theta x1 plus 1 minus theta x2 plus B. But this is also equal to f of theta Ax1 plus B plus 1 minus theta Ax2 plus B. Which is less than or equal to theta times Ax1 plus B plus 1 minus theta times f of Ax2 plus B. So any composition of a convex function with an affine map is also convex. But more generally, if I take two functions, f, g, and h, so f of x is, let's say, g of h of x, where h could be a map from Rn to Rm, and g is a map from Rm to R.
Could you please tell me what
Based on convexity or some sort of a minimal set of properties of G and H.
are convex function only defined on the codomain?
So even if it's defined on a subset, for example, if G is defined only on a subset of R or Rm, I can look at the extended value function, which is equal to the value of the function if it lies in the set and plus infinity otherwise. But for now, let's assume that G and H are defined over all of Rn and all of Rm, just to keep things simple. In fact, let's take one step back. Let's assume that both G and H are real valued functions. So H is a function from R to R and G is a function from R to R. What would be the first approach? Both convex is a sufficient condition. Okay, and how do you get? Okay, let's take the double derivative, the second derivative. So we know that a function is convex if the second derivative is always greater than or equal to 0, right? So what is f, the second derivative of f evaluated at x in terms of the derivatives of g and h? True. We're not aiming to derive necessary and sufficient conditions, because it's always possible to choose two functions g and h which don't satisfy the properties that we're going to have over here. I mean, for example, you could have a non-convex g and non-convex h. The composition could be convex. That's possible. For example, you could take an h which is invertible, take g equal to h inverse of x, then that's a trivial example of a convex function. Okay, what is the second derivative of f equal to? Okay, so second derivative of g evaluated at h of x times h prime x whole square plus g prime of x g prime of h of x times h double prime of x. So suppose that both g and h are convex, right? So then this quantity is greater than or equal to 0. This quantity is always greater than or equal to 0. This quantity is greater than or equal to 0. Right? But is this guaranteed to be positive? Okay. So if you want this to be greater than or equal to 0, then we have to make the additional assumption that G is monotonically increasing, non-decreasing. Sorry? Yes. This quantity is anyway squared, so it's fine. Question?
What if H is decreasing?
What if H is decreasing? So what? If G is non-decreasing, then G prime of evaluated at any point is greater than or equal to 0. So can you give an example of a case where G and H are convex? G is increasing, G is decreasing, and F is therefore not convex. So a case where G and H are convex, but F is non-convex. Minus log and okay. So h of x equal to minus log x. This is a convex function, decreasing, and what is h of x? Minus x. Okay, so
The G of X.
sorry. Okay, g of x is minus x. What is g of h of x? Which is concave. So this is good for intuition, but does this hold in general? What if g and h are general vector valued functions? What if potentially even g and h are don't have these first and second derivatives? can we still claim the same? Yeah.
We can use the definition of convexity.
Yep.
And like h of x, we can split it as theta f1 of x plus.
Sure.
Like, and like to do that split, we will need to use the factor g is from x.
G is monotone.
Like we have h of theta x1 plus minus theta x2.
Correct.
To like write that g of h of theta 1 of x1.
Okay.
Like, so we know h of that theta.
Yeah. So first H is a map from Rn to Rm.
H is not.
Right? H is well again. So H is vector valued, right? So let's assume that each component of H is convex. Right? So H takes a vector in Rn and spits out a vector in Rm. Right? Convexity, as we've defined, is only for functions from Rn to R. Correct? Good point. Yeah. So we'll have to use that. Exactly. So we'll basically use the positive author, the non-negative author. So let's assume that Hi is convex. So what is H? It's basically a collection of maps, H1, H2, up to Hm. So H of x is equal to H1 of x, H2 of x, up to Hm of x. And also I need to basically define what I mean by something being non-decreasing. We'll just use the component wise non-decreasing. So if G is said to be non-decreasing, if G of x1 is less than or equal to G of x2, as long as x1 is less than or equal to x2 component wise. Yep.
The iterator for hi, it should go till m, right?
Yes, it does go to m. So is the statement clear? Any questions? So H is a general map from Rn to Rm. G is a map from Rm to R. We assume that G is a convex function and it's non-decreasing in the following sense. And each component of H is a convex function. Right? So a map from Rn to Rm can be viewed as a collection of m functions from Rn to R. So one example is what, for example, in machine learning, you use, let's say, the softmax function. So you take an input, let's say you take e raised to, for example, following h of x defined as follows. So it's h1 up to hn, where hi of x is just, let's say, e raised to xi divided by summation j equal to 1 to n e raised to xj. So this is one example of a map from Rn to Rn. And what can you say about this? Is it convex, concave? Okay, I'll leave it as an exercise. Check the convexity properties. But now, again, the claim is that G is, if G and H satisfy these properties, then f of x equal to G of H of x is convex. Yeah. Okay, so let's say, again, what we want to show is that f of theta x1 plus 1 minus theta x2 is less than or equal to f of theta times f of x1 plus 1 minus theta f of x2, right? But this is equal to g of h of theta x1 plus 1 minus theta x2. We know that each hi is convex, right? So for each hi of theta x1 plus 1 minus theta x2 is less than or equal to theta times hi of x1 plus 1 minus theta hi of x2, right? So if you view the h vector component wise, h of theta x1 plus 1 minus theta x2 is less than or equal to theta times h of x1 plus 1 minus theta h of x2. And what do we know about g? G is not decreasing. So this is less than or equal to g of theta times h of x1 plus 1 minus theta h of x2. And we know that G itself is convex. So this is less than or equal to theta times G of h of x1 plus 1 minus theta g of h of x2. And therefore f is convex. So let's see some examples. Suppose g of x is convex. What can you say about e raised to g of x? So this is convex. And if you have a bunch of convex functions, let's say g1, g2 up to gm, what can you say about e raised to summation I equal to 1 to m gi of x? Convex. Why?
It's just product of
We've not seen anything about product of convex functions, right? The sum of, so first, summation gi of x is convex because each of these gi's are convex. E raised to, so first the summation of convex functions is convex, and the composition of e raised to x and a convex function is also convex, right? Because e raised to x is a non-decreasing convex function. Okay, if g of x is, say, non-negative or strictly positive, then what can you say about, say, 1 over g of x? Yeah, g of x is convex. Yeah, and convex. Sorry, 1 over x is, okay, then is this convex?
yeah, it's sufficient.
It's a sufficient condition. True. So is 1 over g of x always going to be convex?
This is hard.
X is in R, yes. So we assume that G is a map from R to R plus. Yeah. Okay. Why?
Should be a Gaussian curve. X square plus 1.
Gaussian, I'm not sure.
So, like for example, you take is bar minus square by 1 minus square. That's it.
But that is not convex. Right?
Oh, okay.
G should be convex. Yes.
X square plus 1.
Okay. X square plus 1. So we have 1 by x square plus 1. Is that convex?
At x is equal to 0, it's yeah, it's not convex. It's not convex.
So let's take f of x to be 1 over x square plus 1. What is the second derivative of x?
It is something negative at x equal to 5.
Okay, how do you say that?
Because I know the shape.
Yeah, we are looking at the shape of the curve.
Also, any x comma x and minus x, like if we take them as x1 and x2, line must
Yes.
will be lower than the value.
If you take any x1 and x2,
Let's say some value a and minus a,
okay,
that will be less than 1.
a, okay, yeah. So point is that if you look at f, you know that f of 0 is 1, right? What is, let's say, f of 1 and f of minus 1? It's half, right? So these 2 points, and I take the straight line. So the straight line joining these, so if is f of x always below the straight line joining these 2 points? No, right? Because f of 0 is above the straight line joining these 2 points. Something like this. So it's not convex. Or if you want to convince yourselves, just take the second derivative of f of x, evaluate it, and show that at some point, I guess, at x equal to 0, the second derivative will not be non-negative, to be negative. But you can make similar statements for concave functions, right? So if we go back to the second derivative that we calculated over here, when is, suppose that g and h are both concave, then when will f be concave? If g and h are concave and g is non-increasing, so if g and h are concave, this quantity is less than or equal to 0. This is greater than or equal to 0. What can you say about these two? Okay, so we can have this to be less than or equal to 0. So then I would want this to be greater than or equal to 0. right? So if G is non-decreasing and G and H are concave, then F would be concave. So this is something that we know, right? Suppose that G is convex and non-increasing. Is it still possible to have F being convex? The second derivative of G is greater than or equal to 0. The first derivative of G is less than or equal to 0. Yeah.
How many questions are left? H is linear.
Okay. Okay. Or what if H double dash of X is less than or equal to 0? What if H is concave? You don't need H to be concave, why? Yeah, so it's possible to have G and H being non-convex, non-concave, and still F could be convex or concave. Right? When we're not looking at those scenarios, we want sufficient conditions. That's it, right? So the only assumptions, yeah. So the conditions that we're looking for is if G and H are either convex or concave, and they're monotone in some sense, then when does it lead to convexity? Right? So if G is concave and non-decreasing, and H is concave, so G is concave, non-decreasing, which means that G double prime is less than or equal to 0. This quantity is greater than or equal to 0. G prime is greater than or equal to 0. And H double prime is less than or equal to 0. Yeah? How? With these conditions? Okay.
And actually e power minus x.
E power minus x. But e power minus x is not concave. Yeah. You're right about that particular example. The resulting function is convex. But so suppose I have concave, non-increasing. This is convex. What can you say about the resulting function? It's going to be concave. Again, you don't have to memorize this, but it's pretty easy to derive these just by expanding the second derivative and checking which term should be positive, which term should be negative, for the overall term to be either positive or negative. So as an exercise, just using the properties that we've seen so far, verify whether the following function is convex or concave and under what situations. I equal to 1 to m gi of x to the power p. So just the p norm of a vector valued function of x.
Here,
Right? Or even as a special case, 1 to n xi power p.
that's not
Uh, okay, for all p. So p can be anything between 0 to infinity. And yeah, so what are conditions on g and p for which this quantity is convex or concave? So let's stop here. Any questions? P greater than 1? Yeah, just check.